All right, today is Thursday, May 10th. We've got some handouts here. There are three handouts. One is labeled pressure and, let's see if we can get the exact name. It's called pressure unit conversions, and there's another one called temperature conversions. What I've asked is that the first 5 minutes of class or so, you work on the first three problems. Those answers should be posted to my blog, so please check on the answers. If you get the first three right on both the pressure side and the temperature side, you should be good to go. If you didn't feel comfortable, I'd suggest that you go ahead and work some more of the problems until you're comfortable. At this point in chemistry, though, if I give you the conversion factors at the top of the pressure unit conversions page and the conversions at the top of the temperature conversions page, you should be able to do that with no problem at all. The third handout was the the semester exam packet, which the key for that will be on my blog as soon as I possibly can get it. We passed back papers today, and we're talking about Avogadro's law and Boyle's law, as well as a bit of pressure. Okay, I'm going to skip past this slide, so if you need it, press pause. All right. Gases. We've got certain properties of gases that we need to talk about real quick. Gases uniformly fill their containers, so that means if you put a gas in a container, it's not all going to clump up in the same spot. They're going to spread out and distribute molecules evenly. All right. Gases are also compressible, so if I change the size of the container, they're going to change how far apart they are from each other. They're still not going to cluster together, though. The nice part about compressibility is that, well, we can do some gas grilling in summer, and we can also have clowns make us up nice helium balloons when we go to the circus. They mix uniformly with other gases, resulting in homogeneous mixtures of gas. So that's a nice thing about gases, is that we always get a good mixture. So the oxygen doesn't separate from the carbon dioxide and separate from the nitrogen. And then another thing is that gases have low densities. We realize they've got low densities because we've seen that the air is above the soil. Soil is more dense, air is less dense. Less dense things rise. We've seen that happen when we pour ourselves a glass of soda. We see that the bubbles rise up because they're less dense. Now, just as a quick reminder, density is the result of mass divided by volume. Gases are low density because they have small masses and large volumes. All right. They tend to exert pressure on their surroundings also. You may feel like you're under pressure right now trying to learn chemistry. Fact is that you are under a lot of pressure, like something like 20,000 pounds of pressure right now. Let me explain that. If you've got a postage stamp, think about the size of a postage stamp. It's about 1 square inch. Okay, 1 inch by 1 inch. I call this a 1. All right, so 1 inch by 1 inch. That's a square inch. The amount of pressure that's on you right now from the atmosphere of the Earth is 14.7 pounds for every postage stamp. So if you can imagine a postage stamp on your forehead, and then figure out how many postage stamps it takes to fill up your entire head, that's 100, 200 postage stamps at least. So we're talking about 1,470 psi minimum being pushed on your head just trying to squish you. Okay. If you think you're immune to atmospheric pressure because you're inside, think again. There's cracks, there's windows, there's doors. The atmospheric pressure that's pushing on the atmosphere around the building that you're in right now is pushing on that atmosphere, which is pushing underneath the cracks of the doors, in through the windows, the open windows, and that's pushing into the atmosphere that's in the room. That atmosphere is in turn pushing on you. So you have this entire column of air that's above you that's pushing on you. All right. Now, if we were to talk about this a different way, this is talking about a square meter. So think about taking 2 meter sticks, 1 meter and 1 meter, and figuring out what that looks like. That's a pretty big surface area. That's a pretty big amount of area. Matter of fact, that's your skin is going to be more than a square meter around your body. So when you take a good thought about it, if a square meter is 10 times 10 to the fourth kilograms, that's 10,000 kilograms. If we convert that to pounds, that's 20,000 pounds, because there's about 2.2 pounds per kilogram. So I guess 22,000 pounds is about the right place to talk about that. That's just a huge amount of pressure on you. And now you got to pass chemistry? Whew. All right. So pressure is the force exerted by a gas per unit volume of area. That's per unit of area. That's a pretty simple idea. Pressure is force over area, just the same way as density is mass over volume. Okay. Okay, just to show that we're not mousing around here, this is my demonstration on pressure. I have my bed of nails here, and no shoes on. And remember, stepping on one nail means a lot of force over a very small amount of area. That's a huge amount of pressure, which means ouch. All right. This is a lot of nails, which increases the area. So I've still got that large force, but now I've got a large area to go along with it, which means that the pressure is greatly reduced. Matter of fact, it's so greatly reduced that I can stand absolutely comfortably on this bed of nails. Now, if you don't believe me that this is a bed of nails, I'll pick it up and show it to you. This is something that I created myself, made it myself at home. I drilled out the wood and then stuck the nails through. So these nails are all perfectly sharp, never been used through wood before. Your body has actually developed wrinkles because if you have wrinkles on your body, you're increasing the surface area. So you're actually dealing with the fact that there's larger amounts of pressure. That's one of the reasons why you got wrinkles on your body. All right, that's pretty good. Just for general interest here, I thought this was kind of interesting. We know gases are all around us. They extend all the way up to 120 kilometers overhead. All these gas particles are getting pulled down and they collide with each other, and those collisions are what create the pressure. Pressure is the collisions of molecules with you. That's how you sense the pressure. Fun fact, I think I got this off of Wikipedia one year, 2 years ago. Somebody calculated the mass of the atmosphere to be 5.1361 times 10 to the 18th kilograms. Take a look at this. Thousands, millions, billions, trillions, quadrillions, and I think quintillion is next. 5 quintillion, 136 quadrillion kilograms. You want that in pounds? Multiply it by 2.2. All right. Now, you're feeling a lot of pressure when you think about that, right? But you're starting to wonder, how do we measure all this pressure? All right. This is one of the simplest ways to measure pressure. It's one of the first ways. This is how we measure pressure units in millimeters of mercury, which are some of the more common units that you hear talked about. Millimeters of mercury is what the weatherman talks about when they talk about barometric pressure, or I guess I should say weather person. What we've got here is we've got a dish that has mercury in it. There's atmospheric pressure pushing down on it because there's always an atmosphere on it. At least here on Earth there is. What we do then is we take this tube, this glass tube, it's sealed at one end and it's not sealed at the other end, kind of like a test tube, and we pull a vacuum on the inside of the tube. We quickly put the tube into the into the mercury here. Okay. Now that kind of explains why we call it mercury, millimeters of mercury, but it doesn't explain the millimeters part. When we put this down into the mercury, what happens is this: the atmospheric pressure pushes down on the surface of the mercury, which the mercury molecules, mercury atoms, start pushing on each other, and they push each other up into the vacuum. We measure the height from the top of where the mercury is to the surface of the mercury in millimeters. And this is where we get our millimeters of mercury from. Okay. Now, I said earlier that we're always getting a 14.7 pounds per square inch on our bodies. Hopefully I said it was an average, because saying always isn't true. It's an average of 14.7 psi. All right, so that's our average. When storm fronts roll in, we actually get a higher pressure system. That's how we know that that's one of the ways that we know that the storm fronts are coming in. So we get a high pressure system. What that means is a greater force down, which means a greater force of atoms colliding with each other, which means a greater push up the cylinder. So we'll get a higher measurement of millimeters of mercury off of a barometer when a storm is coming. When a storm is passed, there's always a low pressure front, and that means less pushing of atmospheric pressure, which means less pushing of these atoms of mercury, which means less pressure pushing up, which means that mercury is actually falling. So sometimes you hear the weatherman the weather person talk about the barometer rising or falling. Other times you hear that they talk about the mercury rising or falling. They're really talking about the same thing. All right. I've already talked about these units of pressure. You're going to get them on the test. You just have to know how to use them. All right. Now, when we start talking about gas laws describe what a gas is going to do given that you've done something to it. As we know with all good experiments, you can only mess with 2 variables at a time. So there's actually 4 things that we can do. That means that when you start doing this, well, I could mess with pressure and temperature, or I could mess with pressure and volume, or I could mess with pressure and moles. That's 3 different ways right there. I could play with temperature and volume. I could play with temperature and moles. Ooh, I could play with all sorts of things. I could play with volume and pressure. I could play with volume and moles. Holy cow, there's a lot of different ways to look at this. Some of these are actually duplicates of each other. It turns out that there's 4 scientists that studied gas laws and have made a complete study of gas laws with those 4 experiments. Their names are Avogadro, Boyle, Charles, and Guy Lussac, a Frenchman. We're going to talk about Avogadro and Boyle today. Avogadro, as you already know, is an extremely intelligent Italian man. He has come up with the idea that a certain number of moles, 1 mole, should have a certain number of particles in it. And he's credited with that. We know Avogadro's number. He's also credited with this idea of this law about gases. What he basically said is that the amount of space taken up by a gas should be directly related to the number of moles.
Check it out, 22.4 liters. Special at Walmart. If I want 1 mole, I have to buy 1 of them. If I want 2 moles, I have to buy 2 of them. If I have to buy 3 moles, I have to buy 3 of them. Man, I can't do that math. If I want 100 moles of gas, I have to buy, that's 100 of them.
Numerically wise, we know that 1 mole is 22.4 liters. That means that 2 moles should take up, that's right, 44.8 liters. We can even do this with big math. 10 moles should take 224 liters. Okay, basically what Avogadro is saying is that it's all proportional. This is the equation he's come up with. Volume 1 over number of moles 1 equals volume 2 over number of moles 2. The 1s and the 2s represent a before and a after situation. Usually when we get problems, we're told about things that happened before, so we know both of those. We're told about one of these 2. Let's say we know how many moles we have at the end, and we're asked, what's the volume? So this is simple algebra. We're not going to worry too much about it. Another concept here, along with this, though, is the idea that this is a proportional relationship. Okay, I think I mentioned that on the last slide, but take a look at this graph here of volume versus number of moles. It's definitely a direct proportion. It's a straight line graph. Boyle's law was discovered by an Irish philosopher, Robert Boyle. Basically, what he discovers, think about it as a balloon. Okay, he discovers that if you increase the pressure on a balloon, the volume of that balloon is going to decrease. If you decrease your pressure that you're exerting on that balloon, you're going to increase the volume of the balloon. Makes sense. Okay. The mathematical relationship is this one: P1 times V1 equals P2 times V2. Notice it's a different equation. We're not dividing this time, we're multiplying. Okay, so we can't do the same sort of math here. But the idea here is this: because the math is different, means the graph is different. This is what's known as an inverse relationship. We have a curve, and notice here and here, if you're taking Algebra 2 right now, I say this word wrong, but the graph is reaching an asymptote. Asymptote. I believe that's the right way to say it. Anyhow, it reaches an asymptote. An asymptote basically on a graph is this idea that the curve is going to get closer and closer and closer to that axis, but it is never actually going to touch that axis, which means that the pressure can never actually be zero, no matter how big the volume gets. Okay. On the other side here, the volume can get bigger and bigger and bigger, but the pressure will never actually reach zero. It can get closer, but it's never going to reach zero. And I believe that that is all that we're doing for today. Tomorrow we're going to do a bunch of gas law demos, and we'll talk about Charles' law and Gay-Lussac's law.